Good morning, good afternoon, or good evening, ladies and gentlemen, and welcome to Unit 7.2, or Lesson 7.2, which is all about collisions. First, let's start off by defining a collision. Most people know what a collision is. It's when two objects interact with each other and exchange force, but in a collision, momentum plays a vital component because the total momentum in a collision is conserved. We talked about this a little bit yesterday, so please go back and review Lesson 7.1 if you don't remember what I'm talking about when I mention conservation of momentum. Now, there are three types of collision that you need to know about. The first is called an elastic collision, and no, it has nothing to do with stretchy material. Elastic means that kinetic energy is going to be conserved. So after two objects collide, the total momentum of the two objects after the collision is the same as the total momentum before the collision. You should know that in the real world, elastic collisions don't exist. They're kind of like unicorns. We can use them as examples and to work out problems, but they don't model anything that happens in real life. There are some collisions that are almost elastic, but not quite. There is always going to be some kinetic energy that is quote-unquote lost, which usually means it's converted to other forms like heat or sound. An inelastic collision, which does describe real-world collisions, is one where momentum is conserved but kinetic energy is not conserved. So imagine playing a game of pool with a friend. You hit the cue ball, it strikes one of the other balls on the table, and when it does, you hear a loud clack. Well, that sound that you've heard, that is energy being transferred away from the site of the collision. That energy had to come from somewhere, so it makes a small withdrawal from the total kinetic energy of the system. Also, the pool balls will get slightly warmer as a result of their collision, and that also takes some kinetic energy. So in real-life collisions, there's always some kinetic energy that's going to be transformed into other forms, which means the total kinetic energy after the collision is less than the kinetic energy before the collision. A completely inelastic collision, which is also sometimes called a perfectly inelastic collision, is one where the two objects stick together after colliding. So imagine an arrow striking a target and becoming embedded in the target, or a bullet hitting a block of wood, or two train cars bumping into each other on the track and then coupling together. In a completely inelastic collision, not only is kinetic energy not conserved, but the total kinetic energy after the collision will be at an absolute minimum. So a completely inelastic collision reduces the total kinetic energy to its lowest possible value, meaning it has the maximum amount of kinetic energy that is transformed into other forms of energy. Let's take a look at some examples. We'll start with an elastic collision. We have a red ball over here whose mass is 5 kilograms and is moving with an initial velocity of positive 4 meters per second. Sometimes when we are dealing with multiple velocities, we would use U for initial velocity and V for final velocity. And that's just a helpful thing when we have objects that are changing velocity and there's more than one object. It can get very confusing to constantly use V. So U in this case just represents initial velocity. We have a green sphere over here whose mass is 3 kilograms and is moving with an initial velocity of negative 2 meters per second. They collide and then they move apart. The red sphere now moving at negative 0.5 meters per second and the green sphere moving in the opposite direction at 5.5 meters per second. If you calculate the momentum of both spheres before the collision and then add them together, and then do the same trick after the collision, you get the exact same number. This is what we would expect. This is illustrating the law of conservation of momentum. However, you also get the same thing if you do this with the kinetic energy. If you add together the kinetic energy of the red and green balls before and after the collision, you wind up with a total of 46 joules. That's why we say this is an elastic collision and also an example of something that could not happen in real life. For an example of a more realistic collision, let's take a look at this situation. The balls start off with the same mass and initial velocities. They collide at the same point, but afterwards the red ball is only moving at negative 0.2 meters per second, whereas the green ball is moving at positive 5 meters per second. The total momentum of the system is the same before and after, so the law of conservation of momentum is still being obeyed here. However, the total kinetic energy has decreased. After the collision, the kinetic energy is only 37.6 joules, which is 8.4 joules less than what it was before the collision. So what happened to those 8.4 joules? Energy cannot just disappear. Well, what happened is that energy was transformed into other forms. As I said, when these two balls hit each other, they probably made a sound, so that was some energy being spread out in the form of waves. Also, if we had a very sensitive thermometer or an infrared heat detector, we would probably be able to measure that these balls had gotten slightly warmer after their collision, and that would account for some of the missing energy as well. Here's an example of a perfectly inelastic collision or a completely inelastic collision. After the collision, the two balls stick together. They continue to move to the right with a total momentum of positive 14 kilogram meters per second. However, the total kinetic energy has decreased from 46 joules to only 12.25 joules, a loss of 33.75 joules. So the balls have lost nearly a quarter of the energy that they possessed, and some inelastic collisions they can lose even more of the energy after colliding. So let's take a look at this skill practice question. An arrow with a mass of 0.100 kilograms flying at 70 meters per second hits a target with a mass of 10 kilograms hanging from a chain. How fast is the arrow-target combination moving after the impact? All right, well, we will start off by calculating the total momentum of the system before the impact. So we will call that P-TOT, P-T-O-T for total. And that is equal to the sum of the arrow's momentum plus the target's momentum. Now the arrow's momentum is equal to the mass of the arrow multiplied by the arrow's initial velocity. So I will use U for initial velocity. The momentum of the target is equal to the mass of the target multiplied by the target's initial velocity. We plug in the numbers that we know. The mass of the arrow is 0.100 kilograms. The initial velocity of the arrow is 70 meters per second. The mass of the target is 10.0 kilograms. And although it doesn't explicitly say so, we assume that the target is initially at rest. So we will say that the target's initial velocity is 0 meters per second. Well, you can see what's going to happen here. If the target's initial velocity is 0 meters per second, that means that the target had no initial momentum. So the total momentum of the system is going to be determined by the arrow's initial momentum, which is 0.100 kilograms times 70 meters per second, or 7.00 kilogram meters per second. So this is the total momentum of the system. After the collision, the total momentum of the system is still going to be 7.00 kilogram meters per second. And in this case, the total momentum of the system is going to be equal to the momentum of the arrow plus the target, because the two of them are sticking together and moving as one object. All right, so we can say that 7.00 kilogram meters per second is equal to the combined mass of the arrow and the target, which is going to be 10.1 kilograms. We have to round it down to just one digit after the decimal, multiplied by the total velocity of the arrow-target combination. And now we can divide both sides by 0.100 to calculate that the final velocity of the arrow-target combination is 0.693 meters per second. Now this, of course, is much slower than the arrow's initial velocity, but that's because the momentum of the arrow has now been spread out over the mass of the arrow plus the target. And the target is so much more massive than the arrow that the resulting velocity is much, much slower. This problem is significantly more complicated than the previous problem, and it will take us just a few minutes to work our way through it, but stick with me. We'll find out some interesting things about how momentum works in a collision. A toy car with a mass of 0.050 kilograms moving at positive 7 meters per second strikes a stationary toy truck, so not moving, whose mass is 0.075 kilograms. After the collision, the toy car is still rolling forward at positive 1.5 meters per second. What is the post-impact velocity of the toy truck? And then follow up, how much kinetic energy is lost during the collision? So we have quite a few things that need to be figured out here. We'll start with the fact that the total momentum of the system is equal to the momentum of the car, which I'll call PC, plus the momentum of the truck. Now, the momentum of the car is given by the mass of the car times the initial velocity of the car. And the momentum of the truck is equal to the mass of the truck multiplied by the initial velocity of the truck. We already know that the truck is initially at rest, which means we can go ahead and cross that out. The truck has no initial momentum. And so the total momentum of the system is equal to the initial momentum of the car. So that is going to be the mass of the car, which is 0.050 kilograms, multiplied by the initial velocity of the car, which is 0.7.0 meters per second. I said 0.7.0, I meant positive 7.0. Multiplying those together, we find that the initial momentum of the car, and therefore the complete system, is positive 0.35 kilogram meters per second. We do want to put that positive sign there because that's going to be instrumental in figuring out the momentum of the truck after the collision. But before we get to that, the question also mentions kinetic energy. So let's go ahead and figure out the total kinetic energy of the system before the collision, and then later we'll work out the kinetic energy of the system after the collision. The total kinetic energy, of course, is equal to the kinetic energy of the car, not A, not sure why I put A, plus the kinetic energy of the truck. The kinetic energy of the car is 1/2 the mass of the car times the initial velocity of the car squared. And the kinetic energy of the truck is 1/2 the mass of the truck times the initial velocity of the truck squared. Well, again, the initial velocity of the truck is 0. 0 squared is 0, which means this whole part of the term is going to be 0. We can go ahead and cancel it out. So we have 1/2 times the mass of the car, which is still 0.050 kilograms, multiplied by the velocity of the car squared. And I went ahead and put the positive sign in there because it's a velocity, and velocities are vectors and have directions. But when you carry out this calculation to solve for the kinetic energy is a scalar, which means that the positive sign is not going to be coming with us. All right, so we go ahead and punch all those numbers into your trusty calculator, round your answer down to 2 significant figures, and you find that the kinetic energy of the car is 1.2 joules, and therefore this is the total kinetic energy of the system prior to the collision, excuse me. Now I'm going to go ahead and draw a line there to separate before the collision from everything that happens after the collision. After the collision, we know that the total momentum is still equal to the momentum of the car plus the momentum of the truck. They do not stick together, so we can treat them as 2 separate objects, which is going to be equal to the mass of the car times the final velocity of the car plus the mass of the truck times the final velocity of the truck. Now we'll go ahead and plug in the mass of the car, which is 0.050 kilograms. Assuming nothing broke off of the car, then its mass doesn't really change. Its velocity after the collision is positive 1.5 meters per second, so it's still moving in the positive direction, just slower. The mass of the truck is 0.075 kilograms. And the final velocity of the truck, well, that's what we're trying to find, so we'll leave that as Vt. We do a little bit of simplification in our calculator, and we find that on the left-hand side we get positive 0.275 kilogram meters per second. Now, I should round that number down to 2 significant figures, but I'm about to carry out another calculation with it. So I'll keep one additional sig fig for the time being, and then I will round it down to 2 significant figures after I do my final calculation, which will be to divide both sides by the mass of the truck. And when we do that, we find that the final velocity of the truck is positive 3.7 meters per second. The kilograms gets canceled out. All right, so that is the first part of our solution. The final velocity of the truck, we have found it. Now we need to work out the total kinetic energy after the collision and then find out how much kinetic energy was actually lost. So we will say that the kinetic energy total is equal to the kinetic energy of the car plus the kinetic energy of the truck, which is equal to 1/2 the mass times the velocity of the car squared, plus 1/2 the mass of the truck times the velocity of the truck squared. And we simply plug in those numbers and get our answer. So the mass of the car is 0.050 kilograms. The final velocity of the car is positive 1.5 meters per second. Now the positive doesn't really matter because, as we said, when we get the kinetic energy, we will no longer have a direction associated with it. The mass of the truck is 0.075 kilograms, and the final velocity of the truck, which we've just figured out, is positive 3.7 meters per second and squared. Punch all that into your calculator. I'm not going to go through the individual step-by-step process, but yeah, what you should come up with is that the total final energy is 0.57 joules, which is, of course, less than 1.2 joules because this is an inelastic collision, as we would expect a real-life collision to be. The question asks us how much energy was actually lost. So we will take the initial amount of energy, we will subtract the final amount of energy, and then we will round our answer to one digit after the decimal, which is 0.6 joules. So after the collision, the truck is moving at positive 3.7 meters per second, and there have been 0.6 joules transformed into some other form of energy. That's going to do it for lesson 7.2. Folks, thank you very much for your attention. I very much appreciate it. If you have any questions, be sure to let me know. Please do hop on over to Google Classroom, where I'll have a Google Doc set up for you to do. And as always, I will see you tomorrow when we go into lesson 7.3, which is on the topic of impulse. Until then, stay safe, keep washing your hands, take care of yourself. I'll talk to you tomorrow. Bye.